Testing. Okay, good morning to everyone. So before we start, people was asking me about like how to do the revision assignment. So do I have a template? I don't have a template for you, but you can look up any latex template online. In particular, you can go to Overleaf to find it. Maybe I can give you some idea, but not necessarily you need to follow this. But then this is the framework that you have to follow. But the design itself, I open to you. This is your creativity. So when you tap out, maybe it's something like this. And so there's content where you break the section. And then you type your definition, and then you will type your theorem, proof, something like that. Yeah, examples. Yeah, come up with some question. Yes? Yes, this is a very good argument. But then what they did is like natural algebra, just in a different form. Okay, yeah, let's see something like this. Is it okay? And some exercises, true false, or prove some thing. Right. I put reference. Okay. It's okay. Yeah. Yeah. It's not limited to this kind of template. Depend on your creativity. Make it as adorable as possible. Make it such that your classmate love to read it. But then the content has to be there. The content. So who have to submit first? Let me check the list. Let me check the list. Who have to submit first? Check list. So see. Check who have to submit first. 懂百行业吗？八月, yeah. So because you are just joined, right? So we assign you to type up lecture. Okay. So this help you to revise those. Because you are not here as well, right? Okay, follow the setting that we mentioned. What's your one? And 3 and 4 is 3个月以乘以会以乘以2. Can you start typing out? Yeah, please do it. Now is week lecture 5 and 6, right? So try to submit by this week. Okay, so 1 week after this lecture, try to submit. I will give you a chance to do correction up to the end, but then try submit a draft first. Okay. Is Marie here? Marie keep asking me about the in the chat. So 5 and 6 will be Hong Jia, and I think this guy never appeared. So it will be Jia Wei. So this week 5 and 6, you should go and tell. Okay. Okay. Then you will submit by the end of next week. Okay. For this. And then follow up the rest. Okay. Who? Okay. This is for revision assignment. For your assignment one, right, it's due on this Friday, midnight. Okay, 11:59. Okay, so I don't ask you to finish all the questions there. I just ask you to finish like 60 over 80 of them. Okay, so you have your freedom there. Okay. So some comments from yesterday. Yesterday, say that we want to find the smallest integer n such that n is less than m, or in other words, x is less than m over n. Do you still remember this? So there exists a m over n that is the smallest n such that m over n is greater than this. Okay, so how do we do this? A clean way to do this is we have to use a well ordering principle.
I think you saw this from assignment one, right?
Well, so if X is a non-empty set of natural number,
Then X has a least element. Does this make sense or not? If you have a natural number, set of natural number, then you can find the smallest one. Does this make sense? Because in natural number, what number is the smallest? 1, right? Okay. If 1 is in there, then okay, if 1 is not in there, but 2 is in there, then 2 is the smallest. Right? So this is how you find the smallest. But this is not true for integers, you know. This is not true for integers. For example, if you take the whole integer, right? What's the smallest? No, negative infinity is not the integer number. It's not a number, right? Okay, so you cannot find the least one. Okay, but then you can translate to a sentence that says that if T is a non-empty set of integers that is bounded below. Okay. So what's bounded below? You know bounded above, right? So bounded below is just change the inequality. Then X has a least element. Okay. So if it's bounded below, then it will have a least element. So how to prove this? I put inside the notes already. Okay, so I put inside the notes saying that these two are equivalent to each other. So you should think of this natural number as a bounded below set of integers. Okay. Yeah. Did you guys learn that the natural number is as many as integer? Did you learn countable number? Okay, so you can form a bijection. Okay, bijection between set of natural number and the set of integer that's bounded below. Okay. I put the proof in the notes. Try and read, and then you can let me know. You understand or not? Okay. So if we have the well-ordering principle here, so how to prove this statement is we consider a set of y in Z such that y is less than x, and then this set is bounded below. Okay. You know this set is bounded below by what number? Exactly. So meaning every number is greater or equal than that number. Twice. And x, right? Because you consider all the y such that y is greater than. So nx is the lower bound. Okay, nx is the lower bound. So this is a set of integer that's bounded below. So that means what? That means that this set has a smallest element. But then, in reality, how do you find the smallest integer in reality? How to pick? How to pick? Huh? Right interval? What do you mean? So in the reality, how do you pick actually? So from an Archimedean property, right? What does Archimedean property says? For every real number, you can find a natural number that's greater than it. So you want to find the smallest one that's closest to nx. So what do you do? In reality, for example, okay, let's say you want 3.5, right? And then maybe Archimedean property give you, let's say, 10. So how do you find? So what's the closest integer to 3.5, which is greater than 4, right? So how do you go from 10 to 4? What do you think? How do you go? How do you go? Any idea? And how to go from 10 to 4? Then 10 minus 3.5, and then you get a distance. Good. Then you minus distance. Then what do you get? You get 3.5. But 3.5 is not 4. What? Floor, ceiling, ceiling. Okay. Let's say you don't have ceiling, then how are you gonna determine this? So what you could do is like you take -1, right? So you slowly decrease. Slowly decrease. Okay, is it still greater than 3.5? Is it still greater than 3.5? Is it still greater than 3.5? Right. 4. But then when you reach to 3, right, it's something less than 3.5. Then only you can say that this 4 is the smallest integer that's greater than 3.5. Because the next subsequent integer will be less than 3.5. Yeah. Does that make sense? Okay, so this should be the definition of the smallest integer that's greater than 3.5. Okay, if you decrease one more down, then it will be less than. It's not greater than. Okay. Does that make sense? Okay, so this is in reality you will find that this one. And then this proof is just telling you that it exists. Okay, and then another thing about Chiang comment, right? He says like why irrational plus rational is irrational. Okay, so this proof is kind of very simple. So if you start with the irrational and then you start with the rational. So if you want to show that it's irrational, so let's suppose that it's rational. So then you can write this irrational thing as a linear combination of rational thing. But linear combination of rational thing means what? M over n minus a over b is still rational. And so you write irrational number as a rational form, then it's a combination. Alright, rational proof. Okay. Any more question from last lecture? Injay, do you have a question? I thought last time you said you go back and think first.
Yeah.
Huh? You say you do assignment. Oh, okay, okay. So you finish your assignment already. Yes. Okay, so you finish already. Okay, good. Okay, so you haven't read lecture yet. Maybe. Okay. I just uploaded today. Huh? I just uploaded the lecture today.
Oh.
Yeah. I just finished the editing this morning. How about the rest? Any question? Why are you absent yesterday? Tuition. Sleep. Ah. I thought last time we made a conclusion already. Bring your bag here.
Yesterday,
Huh?
9 a.m. Sometimes.
Ah, I see. Okay. Sure. I'm sleepy as well. But I got an 8 a.m. class of the semester. Crazy. I'm gonna wake up at 6:30.
Yes.
You also have? MBU. Good for you. And by the way, do you guys know a news? Recently news, hot news. Speak Chinese.
Or
Hey, sure. You guys know? How many of you know about that news? Quite a few. Maybe later we can watch the news and then we can try and do mathematical analysis of that news. Okay, later we can discuss that. Okay, during break. Do you guys know why she behaved like that? Do you know why? Anyone know why? No, you just watch the news. Okay, later we will try and analyze the case. Okay. Another thing I want to talk about the P by Q and P and Q thing. Anyone know about Taiwanese celebrities? Anyone know? Only one you know, two know, three know, four know. Not more? Oh, okay, not many, not many. Okay, never mind. So the story is like this. So that celebrities bring a family go traveling to Japan. Then his sister unfortunately gets sick and died. So she was very upset. And then at the same time, she maybe was English she tried to blame herself for bringing the family to China, to Japan, such that her sister died because of disease. So that is her purpose. She implies you. But if you think properly, okay, maybe my belief is different from my parents or my father. Maybe if one person want to die at that time, that person could die a different way. So it's like there's a phrase in Chinese, right? 因为这样子有时间，来的阎王要你
三个字，
三个走对不对？啊，所以感觉比较有可能。Okay, so it could be the case that her sister is just died because of that disease, or maybe she would contract the disease in different cases and die as well. But then she thought that there is an implication. I bring her go. I make her die. You know. So yeah. So then she is very sad in the end. So she cannot she cannot uh, she cannot become a TV host again. So she has a lot of interview interviews those other celebrities. So she cannot work actually for a year like that because she is too sad. And only then now she tried to come out from the tragedy. You understand? Okay, so P and Q and P implies Q is very important actually now. Those are two, and then it will affect you a lot. Okay.
So later we'll watch the Asia thing.
To show you.
Huh? Yeah, it's on Asia. So I think they are trying to fly back to Malaysia from Chongqing. I guess. To Chongqing or from Chongqing? I think from Chongqing. Chongqing is Chongqing. Either to Chongqing or fly back from Chongqing. I think it's fly back to Chongqing. It's Chongqing. Yes. Later we will watch. Later we'll watch. Okay, show you. Okay. So let's resume what we discussed yesterday. Okay. Well, so let's recall a definition of convergent. Definition. We say that a sequence AN converges to L, denoted by leap n go to infinity, AN goes to L, if for any epsilon greater than 0, okay, you can find a capital N depending on epsilon, such that for all the small n greater or equals to that epsilon, we have the distance between your sequence and the limit that is as close as epsilon. Okay, so this one you have to kind of memorize. Sorry. Okay, you have to memorize. This one you have to memorize. Can you memorize or not? Can you close your eyes and then read this? Okay, I give you 1 minute. I give you 1 minute. Then we will close eyes and then we try and read this. Okay, I give you 1 minute. You actually have to imagine the picture. Do you still remember how to imagine the picture? So you still remember the picture? Instead of memorizing word, I think you should memorize picture. Okay, so the picture is this. Okay, so still remember our sequence can draw in a 2D plane like that. Okay, so you have a sequence like this, right, for examples. And then you have a L. Okay. So no matter what strip you have, okay, so let's say I get a smaller strip here, the epsilon strip. Yeah, you will find an n epsilon. Yeah, n epsilon such that for all the terms behind it is living inside this epsilon strip here. Okay. Okay, so maybe I need to recall something for you. It's easier to understand what I say. Please recall this definition.
So if there's a number absolute value of number less than t, then that means this number a gets squeezed between n minus t. Okay, so this is what we do with this epsilon strip here. Okay, so here is epsilon, then this part is minus epsilon. Okay, so your number is living in between this. Does it make sense? So here is okay, I think I should write here. This is L plus epsilon. Here is L minus epsilon. Okay. If I write this thing out, right, so it's just A n minus L
less than epsilon greater than minus epsilon. So an is squeezed between L plus epsilon and L minus epsilon. Is okay?
Can you understand this epsilon strip here? Understand? Understand? AN is in between L plus epsilon and zero. So this one translate to this. Okay. Yes. AN is the term of the sequence. So you can see that. Can you see from this picture here? If I fix this epsilon, find this n epsilon such that all the AN after it will live inside in. Okay. So it is not possible this AN can go out again. If it go out, then we need to move our n again. Does it make sense? Okay, so for all the n, okay, greater equal to this n here, all the AN will live inside. Understand what I'm saying?
They must be decreasing or increasing. Cannot.
You cannot say decrease or increase as long as it lies inside here is fine. But then the decreasing part is make sure by this epsilon greater than zero. Because this has to be true for all. So meaning you can take arbitrary small epsilon. So it's kind of decreasing. But within an epsilon, right, we're not sure it's decreasing. As long as it lies inside this, we call this epsilon strip. Let's call this epsilon strip. Epsilon strip. Okay, so it's like a strip. Ribbon. You know ribbon? Yeah, ribbon. Yeah. For fixed epsilon, we're not sure it's decreasing or not. But then how we make sure that it kind of decrease? Because our epsilon can be arbitrarily small. So if you make your epsilon strip smaller, you still need to make sure your AN live inside that strip. So smaller live inside the strip, smaller live inside the strip until like you get very close to this line. Okay. Okay, good. Okay, close your eyes. Okay, close your eyes. Okay, everyone close eyes. Okay, try and read this. You follow what I say. So we say that sequence AN converges to L if for any epsilon greater than 0 that exists at capital N depending on epsilon such that for all small n greater or equals to this capital N, we get the absolute value of AN minus L is less than. Okay. Yeah. Okay. If you cannot remember, go back. Stick this on your toilet door. Toilet. Watch it. Okay, it's very important this one. Yeah. Okay, good. So next, what we're going to show is a sequence can only have at most one limit. Okay, so you cannot like converge to different limit. Okay, you cannot have two epsilon strip that you can converge. Okay, so how to prove this? Okay, so this is a very analytical proof. Okay, so this is a analytic proof to prove something there's only one of them can exist. Okay, so let's try. But then we still do the same setup. So suppose that AN will converge to two limit. Then we're going to show that these two is the same. Okay, but the way to show it is very analytic. Well, so what do we do here? Well, let epsilon greater than 0. Then, by assumption, so what's the assumption? Just now you read for me, right? Okay, so there exists a n. Okay, there exists an n. Because we got two limits, right? So let's say this n is for k. Okay, so we will write it for k. And then this guy depend on epsilon. Okay, sometimes we write epsilon at the bottom or sometimes we put bracket. Doesn't matter. This is our notation. All acceptable. Such that for small n greater than nk, all the terms should be living inside the epsilon strip. Okay, so what's the epsilon strip? So an, the absolute value of an minus k should be less than epsilon. Okay, similarly for L, the case of L. Okay, you have these two things with.
Okay. So next part is the technical point here. So everyone need to pay attention here. So this is the technical point. So technical point.
Are you sure that this NK and this NL is the same or not? Might not be the same, huh? Might not be the same because NK maybe is 100, NL maybe is 200. Okay, one is 100, one is 200, could be. Okay.
So what's the technical point here is, so we can only say for the small n that is greater than the maximum of these two. Okay. So what to do here? Please follow first. Later I'll explain. So I can try and compare what is k minus l. So well, this part I can split it up into two parts with inequality here. Do you know what am I doing here? What am I using here? Triangle inequality. Okay, so here is the triangle inequality. Anyone can recall what triangle inequality is? A plus B less than or equals to the absolute of A plus absolute of B. Okay, so can you see that what's
A plus B in this case.
K minus?
AN plus AN minus N. So why do I pick this? Anyone know why do I pick this?
Okay, so for example, just now I said this one is equals to 100, right? For example, this one equals to 200, right? So maximum is picking who? 200 lor.
Okay, so I am picking the 200. So if for all n greater than 200, what I can make sure is both term is less than epsilon. Because if I just pick 100, it's not sure that this term will less than epsilon. Because I only can make sure for all the n greater or equal to 200. You understand? Okay, so I have to pick the maximum one. Because if n greater equals to 200, I know a n minus l is greater than epsilon. For sure, this one, this n, if this n greater than 200, definitely greater than 100. So I can have this condition as well. You understand what I'm saying? Okay, if I pick the smaller one, it's not sure that the other one will satisfy. But if you pick the largest one, then everyone will satisfy. And because,
Let me write here. Because n greater than 200 for sure is greater than 100.
okay, so I have these two conditions. Does it make sense?
Okay, so in this case here, so I will get something less than epsilon plus epsilon equals to 2 epsilon.
And Chia want to stop me here. Do you want to ask me why not pick epsilon over 2 here? No need, man. Why no need? Why no need? It's just, it's no need. Okay, okay, later I'll tell you the story of epsilon.
Okay, so, okay, 2 epsilon. Okay, for now we know that it's less than 2 epsilon. So since this number here, k minus l, is less than 2 epsilon, for all epsilon greater than 0, okay? So I have a hack here, maybe a lemma. So I have a hack here. This will imply that k minus the length of k minus l is actually 0. Okay, then this will imply that k minus l is 0. Then this will imply that k equals to l. So here's a hack. Actually, there are two hacks, maybe.
So I let you imagine you have a number that's arbitrarily smaller than all the positive numbers. But then absolute value of a number is what? What's the smallest number you can get? 0. Okay. So this implies that it has to be 0.
You can prove this actually. So let me show you. So let me write down this lemma. Lemma here. So let's x greater or equal to 0. Okay. If for all epsilon greater than 0, x is less than epsilon, then x equals 0. or actually equivalently, if x greater than 0, then there exists a epsilon greater than 0 such that x greater or equals to epsilon.
The first term is what you want, right? Do you agree that this is equivalent? The bottom one is just the contra positive. Okay, because if it's not equal to 0, it must be greater than 0. And then for all become that exists, and then this one change sign become greater. Contra positive.
Okay, so maybe I put a bracket here lah, equivalently, because this is a contra positive.
But then the second one make more sense, right? If x greater than 0, then there exists a epsilon greater than 0 such that x greater or equal to epsilon. What is the epsilon you can pick here? X. Just pick x. Okay. Does it make sense? Does it make sense? Yeah, just pick x here. Or you can pick something smaller than x. Something in between x and 0. X. Okay. Does it make sense? Okay.
If you don't like this proof, okay, maybe okay, I'm proving in this way actually. So proof of this lemma. Suppose x greater than 0, then just take x epsilon equals to x. Then actually x will be greater or equal to x, or actually equal to x.
Or if you want to pick something between 0 and x also works. Okay, something in between.
Can you pick something in between 0 and x? Do you know what's the technique that I teach you last time? How to pick something in between 0 and x? Huh? How to pick?
You remember? The midpoint method. The midpoint method.
Yes. So x. X maybe in this case you want to go to the left, right? So minus x minus 0 over 2, something like that. So actually it's x over 2 basically, because
You are measuring against 0. But in general, you will do this, right? Let's say this is the NP. So in general, you do this b minus a over 2. Okay? And you can be x over 2, also okay. X will be strictly greater than.
okay, so far good. So far so good. Good. Any question? Question at the back. No question? Right. So now I only prove for you for
For epsilon, right? For this epsilon. But just now we have 2 epsilon. Does it matter? What do you think? Does it matter? 2 epsilon. Just now I got 2 epsilon. Here I'm going to prove for you epsilon. Does it matter?
Huh? What do you mean? Say again. Epsilon. What do you mean? Huh? So previously we got 2 epsilon, right? Yeah, what am I writing? 2 epsilon, right? But then here only proof for you for epsilon, case for epsilon. Doesn't matter. Can I use for the 2 epsilon case or not? Can? Let you think about 1 minute. Can. Why?
So it's true.
Because epsilon is arbitrary. Yes.
Replace epsilon by epsilon. That is the same case.
Okay. Can I replace with epsilon plus 2? Epsilon plus 2 doesn't work though.
Because if it's epsilon plus 2, right? You cannot make sure your x is 0. You can only make sure your x is like strictly less than 2. So there's some triviality here. Multiplication works, but then addition won't work.
And so there's another claim here. That you can try and prove, or maybe we can prove together. So for all epsilon greater than 0, if m less than epsilon, if and only if, let me see. I just say that there exists an n in r greater than 0 such that for all epsilon m less than n epsilon. Okay, so you can prove this actually. This proof is not hard actually. We can prove it together. Okay, so if you know that something is bounded by some n epsilon, then for sure it can bound by epsilon. So how to prove this? So which direction you want to do? Left to right or right to left first? Maybe let you pick. Maybe ask Yushen to pick. Yushen was not here yesterday. Yeah, pick one direction. Left to right or right to left? Left, right. Okay, good. So left to right. So left to right, what do you need to do? You need to find an n, right? Okay, you need to find an n that works. Find an n that works. What n works? What do you think? So if you have left already, okay, so what n will work here? Can compare this term and this term. How to make it the same? N need to choose one is enough. Okay, one is enough. So this direction actually is quite trivial. Okay, so fix epsilon greater than 0. Then let's see, how should I start this? Is my direction wrong or not? So I think let's change this direction. Change this one. I think something wrong. Something. Let me see. Yeah, let me think first. For every epsilon. Okay, this doesn't depend. Okay, so this doesn't depend. So maybe I should do. So let me see. So fix epsilon greater than 0, then set. So actually we just set n equal to 1. Then for all epsilon greater than 0, m is less than equals to epsilon, given by the left condition. Okay, so this direction is very trivial. How about the other direction? Okay, the other direction will involve what Tianle said just now. Okay, so let's say you have a n such that for all epsilon greater than 0, n less than n epsilon, but then you want to make it become epsilon only. So what can you do here? Okay, do here. Okay, so you need to start with this epsilon, okay, and then try to use this condition, and then to help you get this equality. So you need to assume this, use this, prove this. Okay. So here's your assumption. So let me write down. There is assumption. Assumption. How to write? Assumption. Okay, here is also assumption. And then this one is go. Are you guys confused with these two epsilon? Are you guys confused with these two epsilon here? Are you guys confused? Are they the same epsilon? What do you think? What do you think? Are they the same epsilon? These two epsilon, are they the same? 一样还是不一样？两个罢了，选一个，一样还是不一样？讲啊，不用紧，错不用紧啊，不会打你啊，我没有带坑边。Yes, they can be different. For example, I can change this term here to for every gamma greater than 0, m less than n gamma. Can, doesn't matter. 可是懂我讲吗？明白吗？ They appear in different sentence, so we don't really there's no really a connection there. Okay, it's just saying that there's a real number greater than 0, then m have to be less than n. That real number. 没有关系的。So sometimes you need to be careful.
So a very good question asked is there, right? So in assignment one, the axiom of the classroom, right? There's a pair of students, axiom D, C, okay. So I already edited in the document. It has to be for every pair of distinct students. Otherwise, if the student is the same, then the axiom will be degenerate. So you cannot prove what we wanted to
他
prove.
还讲哦，那个 pair 是不是我的
它的 pair 是不是什么
我的 pair？
？order pair。
还认为哦，跟你们分享。如果是他是我的 pair 的话，我有很大的是
order pair 我的 pair 没有吧？应该没有。
pair 就是联盟啦。
这
Pair for more students and for more students, why? Like given like for every pair of students, you fix.
Yeah.
Yeah, for every pair of students, for every student X, for every student X, for every student Y, something. It's not here.
这样子，孟主任谁有啊？你我们欧讲，我这个 pair 是不是讲过？
你的意思说是阿丽跟阿布跟阿布跟阿丽是不一样的 pair
我的 pair 是这一次啊。
啊？这样是 order pair 是可以吃啊。
把那比较一样嘛，反正这个后面写的问题都是这样，你到咯，我们这里一点不这样用。
Okay. We can discuss it later. So doesn't matter. Okay, these two epsilon is different. Okay, can make sense?
Okay. So what do you do here? So obviously you want to prove for all, right? So you need to start with arbitrary epsilon greater than 0. Okay, so you fix epsilon greater than 0. Then what? Then you have this condition here. Okay, you have an n. Okay, and then if you start with any gamma greater than 0, then m will be less than n times this gamma. So is this epsilon one of the gamma I can pick? Can or not? Is it one of the gamma I can pick here? Can, right? Because epsilon greater than 0, you say for everything greater than 0, right? Okay, so let's say if we choose gamma to be epsilon, then m will be less than n times epsilon. Is this what you want? What's your goal? What's your goal? Your goal is less than epsilon, no? But then you get n epsilon. No? What's the difference between n epsilon and epsilon?
No. Don't tell me that first. I'm asking you what's the difference between n epsilon and epsilon? What's the difference?
So n times epsilon.
Good. You have an extra n, right? 不要笑啊，这个很重要，不要笑，这个真的很重要，这个很重要，这个很重要，不要笑，真的就是 epsilon n epsilon 就是有一个 extra n 在那边嘛。How to remove this n? Is there any way to remove this n?
Divided by n.
Divided by n,
If n is non-zero.
If n is non-zero, but then n is non-zero, right? N is non-zero, right? Right. Yeah. Okay. So I divide by n, right? So how can I introduce this divide by n into somewhere here? Can I do that? How?
Times n over.
Let gamma be epsilon over n.
Okay, I don't choose epsilon. Epsilon not nice, ma. I change it. Change it to epsilon over n. Then here will be gamma again, ma. Epsilon over n. Then there will be epsilon. Then this. Can you verify that this is again greater than 0? Isn't it? This is what we did in the consequence of real number. So we have epsilon greater than 0. We also have 1 over n. So n greater than 0 implies 1 over n greater than 0. So it's closed under positivity, right? Still greater than 0. Okay. Does it make sense? This part here. Okay. Good. Okay. So this is a very special property about this less than n epsilon thing. You cannot do epsilon plus something else. That one is a different thing already. Okay. In that case, maybe you can ask me, can I make this epsilon instead of 2 epsilon? In that case, can I make this epsilon instead of 2 epsilon? How?
I mean this divided by n over 2. Not quite, not quite, not quite. The n should be depending on
Epsilon over 2 now instead of epsilon. Okay, so instead of epsilon, you should pick epsilon over 2 here. Then this one will become epsilon. This one will become epsilon. Okay. Does it make sense? Okay, so in this case here, instead of you forcing your terms is epsilon close, you take the epsilon over 2 strip. You make the strip smaller. Okay. Does it make sense? Okay, so
this. Sometimes this is for aesthetic purpose. You know what's aesthetic? Xi'an, aesthetic. Aesthetic. So 你讲的 yeah, beauty. Okay. So instead of a multiple of n, multiple of epsilon, we choose these epsilon such that we end up sum to a nice epsilon. But then how do you choose this actually also telling you that this calculation actually depends on how many components. Okay? You understand what I said? For example, this calculation depends on 2 components, right? So you need epsilon over 2. And maybe in future you need 4 components. So maybe you need to make your epsilon strip even smaller. And epsilon over 4, for example. Does that make sense? But if you don't pick, also never mind. I already proved to you already, right? As long as it's a multiple of epsilon, then you are good. Does it make sense? Yeah. Okay. Question?
okay, good. Okay, good. So then we prove that this works.
This direction for people for question. If you have an absolute value that is equal to 0, then it has to be 0. The thing is like that. I'm not sure you learn in the linear algebra of absolute value of a vector is 0, then that means the vector has to be 0. You learn that? Or you recall that? We prove this. You can prove this by contradiction actually. If it's not 0, then the absolute value is not 0. Okay.
Good. Okay, so we are done with these things. Okay, so what time is it? 12:45. 12:55. Okay, maybe we can take a break here. Okay. So let's break. Let's break until 1:04.
Okay, initial.
Okay, okay. Let's see the action. Okay, I'll show you. I'll show you.
那个机那个飞机上面拿。
No English, no English. I'm China. Bro.
Maybe I show you a sequence of videos, and then you try and guess why that woman try to argue. Why the woman argue like that?
Just mute this. 是不就是不是不一定，或者是不一定。
他在飞机。
不懂，但是
来找谁？
没有
还要
飞机啊，那我们
就一个，不会说中文。你很像我呗。
你在拍照是？没有，后面那个有一个摆着那个还第一就是会讲哦，
你看到他的素颜，素颜不是那个他在
啊，他
讲他自己申请那个女的。
这个眼睛然后自己拍一个第二个名字。
你去看什么？
是，
看我现在看，我现在看，现在看，现在看
不是学习咩？
，break 了，break 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 了。什么？进来，等下声音加大声。
现在你们 follow 他 IG。
我操，
你要变成你 ID。
没有。
你知道我昨天两人的情况，那个。
OK。看了吗？看到了吗？你们猜为什么他跟他吵架？没有，没有，这段里面都没有这个。你们有听完吗？有听完整个东西吗？要不要再玩一次 ？OK， 再播一次，再播一次。OK，so from here，你猜他是为什么跟他们吵架？你猜？哦，使用国际化会讲中文哈，还有嘞？还有吗？啊？他被投诉，对，有拍照对吧？还要他删掉之类的。OK，然后我们看一个更完整的影片。OK，这个影片，这影片是被剪出来的啊，我们再看一个更完整的影片，然后我们再想一下为什么他要这么闹。啊
他这句话跟他过后的一句话有关关联是吗？
OK，等一下我们可以讨论。
但是他也不敢。
OK，I think 应该是这样。说有那个重点嘛，有一个重点有听到，或者小细节啦。先讲一个小细节，你有没有听到他讲什么？我有4个朋友，他们上不了飞机，就我3个人。
搞这个生活。
你没有听到？他有一个很重点、很大声的 part，他讲就4个人没有上到飞机，就我上到飞机这个是导火线。为什么？因为他在飞机里面讲话很大声，因为他 call 他朋友嘛，他朋友上不了飞机嘛。然后因为他也不是讲他讲话很大声，在里面啊被人家拍起来，然后人家 complain 他，然后就开始吵。所以其实这个 China 不 China 不是重点来，重点是他朋友上不了飞机，他也不打算飞了。其实，所以你看他一直的诉求就是说，哎，现在你就是赔给我就对，你讲看你讲赔给我。我可以让他们走，我可以不要走。对，他们可以走，我可以不要走，但你一定要陪我。他觉得他朋友上不了飞机是他们的问题。OK，全部新闻的重点都是拍在这个 China 啊，讲华语不讲华语啊。但是他的诉求就是他的朋友3个朋友不要上飞机，明白吗？他可能拖一下，可能他朋友可以上飞机，因为我不知道，明白吗 ？OK，Yeah，you understand？明白吗？所以有时候啊，你们吵架或者你听别人吵架，可能那个东西是重点啦。当然这是新闻嘛，新闻肯定是剪一些比较 catchy 的 part 给你看。泡米团对啊，什么？对啊。
但是他打电话，人家不一定会拍他。如果人家会拍他，就不会有这种事情。
应该是可能太大声了，人家跟他讲人家跟他讲要起飞了，不要再用电话，而且他又讲得很大声，然后他还可能不听。他你如果注意仔细再去看那个 video 啦，因为我这个声音不好，他有说过反正飞机还没有飞嘛，我可以打吗？打到飞机飞上去我就打不通了哦。他是这样讲的，他是这样原话是这样讲的，可能我是讲到比较马来西亚吧，他原话是这样讲，对，所以人家就不开心哦，人家不是做 evidence 说，你看你飞机飞了，你还在打电话，有几千万的粉丝还是什么这样很多人还有然后就开始吵，空服人员就过来了，That's why 才有这个 speak Chinese speak English 的片段了，因为那个空服人员跟他讲英文，跟他讲这里是 China 什么什么，所以他其实在纠结另外一件事，但是人他吵在另外一件事，你 understand？ 他纠结是他朋友上不了飞机，因为朋友上不了飞机，本来一起飞的，变一个人飞，可能一起去玩，变一个人去。对啊，
他们跑吧，好像是去铁路，
是不是啊？应该是重庆回来，重庆来回来。
你要对下一个后手感。
3个，OK， 自己回家看。啊？我什么阿力？OK，so yeah，so 就是这样的时候，when you like 你要 discuss 一个问题的时候 ，try to get to 那个问题的中心点，不要被那种 side problem 带走。OK，try to 问一下为什么他这样。
因为你吃饭。
拜拜。OK，yeah，OK，yeah，拜拜，yeah。then 这个东西it's very important in analysis 啦。OK，so don't try to get distracted by side problem. Okay, try to get back to the original problem. What are you trying to get? Because usually you get distracted by some technicality, but then those are not too important in this type of thing. Yeah, because the big picture, like if you write down most of the step is correct, then you'll get most of the marks already. Yeah, the technicality is something you need to brush on. Not easy to get, but then at least you need to get the big picture. This is about pure maths. Okay, pure maths is about logic. So we want to link things together. So maybe you might see there's a comment like, oh, mathematicians don't know how to count. Sometimes it's very true because we usually focus on the connection instead of the calculation. But then calculation is important as well. But then sometimes people will be careless or something.
Just use
Yes.
computer.
You just something like that. You just use calculator, right? Yeah. You can give computer to compute, right? Yeah. No, sometimes you have to give it to them, I can recall in my PhD research, I need to use mahjong paper to do my calculation. Because the thing that I want to calculate is too large to draw already. It's not enough to draw on the A4 paper, I need to extend my A4 paper, use the glue, use the sellotape, tap. So might as well use mahjong paper. Yeah. And then there's one time I stick all the mahjong paper on my wall because I want to see them. Yeah, that's a side story. But then there's the time when I do research.
这两口钱。
对，没有错，上的口径。Okay, good. Then in that case, can I see if I can sign out the online attendance? Let me try. It seems to be down just now, but then I'm not sure it's up or not. If not, I already take a picture of you, so I can take attendance later. By the way, tomorrow is a tutorial, right? Okay, so it's also down. Okay. Then I think no need. I think I also don't need to do. And I'll just take the manual one. So what do you think if I ask you to do presentation? Do you know what am I looking for? By the way, I started my class. So if you can enroll, you just enroll. If you cannot enroll, then never mind. I think WeCom is down, but the mobile version is okay. Yeah. I think I heard them saying mobile WeCom is down, but then mobile version is working. So you can try and sign in if you can. Do you know what am I looking for when you do presentation? Am I looking for correct solution or wrong solution? What do you think? What are you thinking about? Okay. So there's a famous quote by other mathematicians. Maths is an art of giving different names to the same thing. Mathematics is an art of giving different names to the same thing. Okay, so just now I said presentation, right? So you should say another thing to talk about this presentation. So what am I looking for is your I don't want to say presentation. Your how you express your idea. Okay, either it's wrong or right, doesn't matter. Do you believe in your idea or not? Or can you correct your idea on the spot or not? If it is wrong, if it's correct, can you defend your idea? How do you defend it? Do you just argue? Do you just do like what the woman do just now? 你给我说清楚，我错了什么法律？对不对？ I think this attitude is good, but then she's wasting people's time, right? So you need to adjust yourself. How do you deal with this kind of situation? You understand? Yeah. So this is what I see in your presentation. I'm not looking for 100% correct solution because the solution I know already. I don't need you to tell me. I just want to know about you yourself. Okay, how you express your own idea. Either it's correct, either it's wrong. Okay, if it's wrong, then how do you correct it? If it's right, then how do you defend it? That's why we have something called the thesis defense. So in future, maybe you need to write a master thesis. Even FIT could be a thesis. So you need to explain your stuff to people because your stuff is very new, right? So people could be skeptical, saying that, oh, does this work? This work, man? Oh, does this work? Can man? Like that. Okay. No, there will be more harsh than this. Doesn't work. Yeah. So you need to defend yourself. Okay. So this is what I wanted to see in your presentation. Okay. It's not about correct. It's about correct solution, but it's not all about correct solution. Okay. So another thing is try and attempt the question first before you come. Because as you experience, right, 30 minutes is quite short if you just want to start from scratch. So try and get all the relevant definition ready first, and then you can start discuss. But then there's another good point is some of you before you come to tutorial, you finish all the questions. But I don't know how you finish. So for example, the girl at the back there, front there. What's your name? 尹恩，遗憾，对，遗憾，还有天乐也是。Okay, surprisingly, two groups got at least one. Very surprised. Yeah, very good. Good practice. But then it's not that you finish all, you come here, then you don't discussing. So you try and discuss with your friends. Okay, maybe there's some point that you want to clarify. Okay.
Very good. Okay. In that case, let's continue. Yeah.
I'll learn about you again. I will take the attendance on myself.
Okay. So next, we will talk about divergent. So we talk about convergence, right? Let's talk about divergent. So what's divergent? We know converge, right? So then it's negation of conversion. So a sequence does not converge is called divergent. There are different way of divergent, by the way. Okay. So there's a way called the diverge to infinity. Okay? Diverge to infinity. So we will say that a sequence diverges to infinity. Let's use the mathematical term to talk about it. I don't want to write down the English. That is, for all m in R, there exists a capital N. Okay, maybe depend on this m, such that for all little n greater or equal to nm, an is greater than m. Okay. Can you agree with this? This sequence look diverging. I don't know.
Because your m can be very large. Right? Should I fix my R? Let me see.
Maybe that was
Oh, no, never mind. Okay. Sorry. Yeah.
maybe like we just most big.
Yes. So the infinity here we're referring to positive infinity actually. So this infinity we're referring to positive. Because you can imagine that if I pick like a million, then you still have 100 and 1 million. Then you go further. Greater.
Then we say that sequence diverges to negative infinity. Maybe I write here infinity. By the way, this thing is not in R. Negative infinity. If for every m in Rn, what do you think? What do you think? This is a capital N, such that for all little n greater than nm, we will have am smaller than m. So you can push all the an down. So in these two cases, this is what we write as the limit of n to infinity of an equals to infinity, or limit of n to infinity an equals to negative infinity. What do you think? Why do I need to define this limit separately from just now? What do you think?
Why should I mention this? And then replace the L with infinity. And replace the L just now with infinity.
No, because L is because in this case infinity for real number.
Yes. Okay, so in this case here, L is not a real number. Infinity is not real. Negative infinity also. And then the way it kind of or whatever is different, right? It's different. There's no epsilon here. Makes sense?
Okay. So can you imagine the video that this theorem trying to tell you? So if you fix an M1, there will be a n epsilon M1 such that all the term after it should be greater than this M1. Okay. Fix another M2, then you can find an n epsilon not epsilon n M2. Here is the n M1, such as all the term here is greater than M2. So that's why you can keep pushing your terms up. Okay.
If it's negative m, it doesn't matter. Positive and your terms will live above it. Okay. For the one that live below it, then the negative one will be more important. Okay, push. Does that make sense? Yeah. Yeah. Because can you imagine that your AN could just start here? So if you pick any lower M, will automatically satisfy, immediately satisfy.
So let's give some examples. Let's give some divergent sequence. So let's give one example. So let's consider an equals to n. I think yesterday we talked about this, right? Okay, so what do you think? Does this converge or not? Can you find an L such that for all epsilon greater than 0, then every term will live inside that epsilon strip? Can you imagine first? So what's your sequence? Try and draw it. 1, 2, 3, 4, 5, like that. Right? Okay, can you find an L such that the epsilon strip,
All the sequence will lie inside the find it. Can you find it? Move L, then move your epsilon strip. Give me yes or no. You have to decide. In this class, mathematics are only true or false. Yes or no? No, right? Because no matter what L you no matter what epsilon you pick, there's someone that's outside the strip. Correct? There's someone outside the strip. How do you prove that? Yesterday we have this fact, right? Archimedean property. You can have a natural number that's greater than this real number that you use. And you can pick the top one that's the natural number greater than.
okay, in that case, we're going to prove that instead, we will prove that an diverges to infinity. Okay. So what do I need to do to say it diverges to infinity?
So for any m, I need to pick an m. For any m, I need to pick an m.
Okay, such that this inequality holds for all the little n greater than nm. So in that case, I have no choice. You need to check for all m, then you need to start with any m. So let's start with any m. So let's pick m in n. M in R, sorry. So what do we want to show? We want to show that we can find nm in n such that if n greater or equals to nm, implies that an greater than m. Okay? But then what is an in our case? In our case, what is an? This is by definition what? An. What's our definition? An equals to n.
So you want this or you want this, right? You want this. You have this. You want to pick your nm. So what nm to pick so that you have this line. M is real, right?
What am I doing here?
Oh, okay.
Yeah.
So say again. What do you say? Say again. M plus 1. M plus 1. This M. M plus 1. But this nm need to be natural number form. Okay. So this m is a real number. Real number plus 1 maybe it's just another, might not be natural number. Right. So everyone know what to do here? So this is given, m is given. You want to find an m. Okay, such that if this is true, then this you need to prove is true. You need to have your n greater than this.
This natural number greater than n.
Okay. No need list, right? We just have the Archimedean is enough. So by Archimedean property, we actually can find, let's call it any number I haven't used for here. Let's call it B or A. Find an A in N such that A is greater than F. Okay, this is not agree, everyone? Does it agree? Yesterday we do this, right?
For every real number, we can find a natural number. That's great.
Then I say pick NM to be A. Okay, so we need to check now. So we are checking. So let's check. Does it work or not? Okay, so now we do checking. So let's do checking here. So suppose N greater or equals to NM, which is A, but then we know that, how do we pick this A? A is greater than M. So N greater or equals to A greater or equals to M implies that N is greater than M. Let me see. Am I correct? Yeah. Then we are done. So as desired. Okay. Does it make sense? Any question? Question?
Okay, so the choice here you can pick, but then you need to check whether it's correct or not. So you check whether you get the 4. Yeah. Any question? Yeah, so you can find the smallest one, but then not necessary. But then this smallest thing is what analysts like to do. They want to find a smaller bound. They want to bound it smaller. But I don't care. I don't risk. I can achieve my goal. I'm happy. I'm an algebra. Analysis will try to find a smaller one. This one not good. Smaller a bit. Smaller a bit. Smaller a bit. They try and improve the bound. This is what they're doing for their life. Improving bound. Improving bound. Okay, but then everyone okay with this proof? Yeah. Okay. Any question? No question. Okay. So you see, this Archimedean property is very important. We'll be keep using it a lot. Okay, a lot.
Okay. Right. So maybe an exercise you could do. Okay, so you go back and try and do exercise, prove that this an equals to minus n diverges to negative infinity. Okay, try and prove this. Okay, so it's the other direction. Okay, try and do this yourself. I have a solution in my notes. I think you can try and compare. There's another sequence that's not divergent, but not diverge to infinity or negative infinity either. Okay, so let's look at this one. The alternating sequence between 1 and -1. Okay. Can you prove that this is divergent? Is it possible? So maybe let's draw the picture up so that you know what's it. Okay, is it possible to prove that this is not convergent? So to prove that it's not convergent, what's the definition? Maybe Pingjie can tell me. Negation of convergent. What's the definition you need to show? Yes. Yes. In N. Start with convergent first and then negate it. What is convergent? Just now I asked you to close your eyes and then read.
Epsilon greater than 0.
For epsilon greater than 0.
N in natural number.
Oh, you need to pick n first. There exists an n.
Exists an greater n.
Okay.
That belongs to
Natural number. Then
A n minus L is smaller than.
Okay, so if divergent, so negate of this thing.
For all epsilon greater than 0,
For all negate becomes what?
or
That exists.
or there exists a greater than 0,
Then
then there exists n inside.
there exists or for all.
I need to write it down.
Write down. Okay. So the full definition of convergence, where is it? Let me see. The full convergence. Okay, here. So actually, if you realize, there's something about this L, right? So this L should be there exists an L in R. Okay, so if you negate it, you pick any L in R. There exists an epsilon greater than 0, such that for every n epsilon in n, how to negate this? I think you tell me how to do it last week, right? Becomes P or
Not Q.
after negate becomes not P.
P.
Okay. Let me write down first so that I don't confuse myself. So P implies Q is logically equivalent to what? P or, right? Not P or Q. Not P or Q. Sure? Anything about it? Okay, not Q. If it is not P, this is always true. Okay. If it is Q true, then this is always true. Okay, I think right. This is right. Okay, so then not P implies Q will become P and log Q. Okay. So if you negate this, is either n greater or equal to n epsilon n and such that n this is every and we need to quantify this n. Yes, we need to quantify.
So this one become there exists for.
We need to quantify this n. So this, I think I should say for all n in natural number, if this happens, exists with n, such that if this is true, then the negation of the so that is this is full. Okay, so the full sentence is like this. So there exists an L in R for all epsilon greater than 0. There exists an n after n depending on epsilon, and such that if for all n in n, if n greater than or equal to n epsilon, so this n is a smaller n, then L the an will live inside the epsilon string. One. Okay. Right. Okay. So can you prove this? Prove the negation. Okay, so if you look at this sequence here, where's the sequence? Yeah. So if I give you any L, okay, if I give you any L, okay, can you find an epsilon such that no matter what n I give you, there exists a further guy that is not living inside the string. Okay. I think you need to break into cases, actually. You need to break into cases.
But you may do a projection.
How? I'm trying. Even you contradiction also need cases. You need cases. Only.
这里有答案，有吗？
What so难？这么难？我不知道我怎么难。
你要听。
我有答案，
我有答案啊，
我有答案。
What's the
我可以 prove by case 吗 I mean like I can fix my L is not one. I'm not sure whether it's necessary to break to case, but then it's natural to think as case is
think that if I choose L as 1 and minus 1, there will be the same way to analyze. If I pick L that's not 1 and minus 1, it will be the same way to that's what I thought at first. I need to write it down first and then try and compare whether these two arguments are the same. If they are the same, I can combine. If not the same, then I need to separate. This is a natural way to think about it. You know why I separate into two cases? Because if I pick L that's not 1 and minus 1, I can easily pick epsilon that avoid all the points in the sequence. But then if I pick L to be 1 or minus 1, then you will have point that's living inside this epsilon, but at the same time you also have point not living in the string. And then you need to write that down. You understand what is it? You understand what is it? Hello. 听不懂的话，回去写上。Try to practice 写上。I think 我也会写上。可以。什么 conversion 你要讲？
大家是一个大家是这个 sequence 是 converge， 就是converge 属一个 arbitrary 的
arbitrary 不可以的，
就是是吧？
那个
假设是一个主一个
OK
假设 A 啦吧，
OK
然后它 choose 一个 epsilon 是小于 1， 因为那个 epsilon screen 的那个团队就会小于2，
对，
然后就不会就只能覆盖其中一个部分，就是上面
最多只覆盖其中。Okay. Yeah. So this is the idea, proof idea, but then you need to try and write it down in the mathematical form. So the proof idea is 8 epsilon to be 1. Let's say 1. Not be 1. Or 1 to be leaving. But then we care about less than though. Because some of the definition okay, maybe
I can maybe I can challenge you. There's an equivalence definition
where I can replace the strictly less than become less than or equal to. Yeah, equivalent. You can try for this. If you replace this definition with less than equal to, these two definition is equal to. Right? And you can measure one and then the other one will always. Do you know what I said? What I said is I replace with this with x less than equal to doesn't matter. It's the same thing. It's equivalent, the two definitions. Okay? So make it into exercise. Okay.
Okay, this exercise is very important when I say in class because I have in mind how to do it.
So if you don't try and do it, sometimes it will appear in your quiz or appear in your test, and you will cry. Why I don't try before? So please try now. When I ask you to try, please try.
Next week got quiz, yes.
How I think.
How about until next week?
Quiz 2
Quiz 2 what do you think?
If I cover until this week, is it okay? Whatever with today, is okay? Yeah. So okay. So in that case, would be every quiz will be the previous week stuff. Okay. Good. Or if I have quiz next week, then that means there's a previous week stuff. Okay. Good. Okay, so this one we left as an exercise, and then we try and check with the notes later. So this one make it an exercise. Okay, 140. Good. Okay, next we'll talk about what's the next thing you learn in sequence. Do you still remember? Calculus, limit law. Okay. So suppose you have two convergent sequence. And converge to L and Bn converge to M, then we can look at the sum of sequence. It's again a sequence. Okay, so these two n has to be the same. A1 plus A1, A2 plus B2, A3 plus B3. Okay, this is what this means here. So this will converge to L plus M. And then if you scalar multiply your convergence sequence, then your limit will get scaled with the same factor. If you take the product of two sequence, then the limit is just the product of two limits as well. Then there's another thing about quotient. If m is not 0, then Bn should be non-zero for sufficiently large n. Do you know what this means here? It means that maybe your B1 is 0, B2 is 0, B3 is 0, but then your Bn cannot be forever 0 because you need to converge to something non-zero. So somehow your Bn should like go towards that n. Right? Because your epsilon stream get very close to them already. So all your An should stay there. You understand? Okay, so let me draw the picture to you. So when I tell you the story, right, you should imagine an animation in your mind. Okay, so for example, what I said just now, what you should imagine is something like this. So you have 0, right? So let's say this is B1, this is B2, right? But then your M is non-zero. So maybe let's say greater than 0 here. So your convergence says what? No matter how small your epsilon B, right, your Bn should stay inside here. Right? So no matter how, for sufficiently large n, it should stay inside.
Epsilon stream or so eventually your Bn will be.
This is what it means. Then I can consider An over Bn whenever this term here makes sense.
And maybe the first few terms doesn't make sense, doesn't matter, but then for sufficiently large, this will make sense.
And then this will converge to L over N. Do you see this law as a nice consequence? Do you see this law as nice consequence? You know why is it nice? Why is it nice? You need to start to learn how to appreciate these results. So why is it nice? Why?宜兴的旁边是谁？是谁？子晴哈，子晴 ，OK。Why is this result important? Or maybe nice? Why is it nice? Why people think it is nice? What do you think? It's a structural question. There's a structure here. No, not really. Right. Yeah. Okay. Then, yeah, sure. You can do addition. Yes. Oh, I did.
Can we say? Because we can distribute the limit into each term and then of the limit.
So
Each. If you find the limit of A and Bn is difficult, but if I can find the limit of A and the limit of Bn, then it is easier to solve the limit of A and B.
and type Bn or
Okay, maybe solve the limit of A and Bn.
which one? A, Bn, this one.
Yeah, this whole term.
Yes, it's okay.
Maybe it's more difficult.
Correct.
But maybe if solve the limit of An and the limit of Bn,
Yes,
is easier than
that's right. That's right. Even more than that, more than that is the limit that you convert, right? Respect the operation you take on the sequence. Understand? It's not like An times Bn go to L plus n. No. It sometimes will happen that thing. It's like exponent multiply become plus. That could happen. But then here, the limit respect the operation that you take on sequence. So if you have a sum of sequence, then you will convert to sum of it. If you have a product of sequence, you convert to product of it. If you have scalar multiple of sequence, you convert to scalar multiple. Understand what? Okay. Yeah. FGM and
sounds like being operator or something.
almost.
Like it's always on the pizza or something. Like you take limit as a function and then
Oh yeah.
it's
Yes. So limit, yes, definitely limit. Okay, good. Actually, that's a good point. So limit actually is a linear operator. Limit is a linear operator. And from here you can see that actually limit is a linear operator. Yes. Limit is a linear operator. Because here say that limit of an plus bn is limit of an plus limit of bn. That's right. Limit is a linear operator. Then from here, for these two two. This one is like algebra already.
Okay. So what time is it? 1:47. Okay. What should we do next? Did you guys see this in calculus 1? You see this? Did you guys prove it? Function. Oh, right. Okay. Do you use epsilon delta to prove it? Oh, you use epsilon delta. Okay, yeah, sure. Okay, very similar. Actually, very similar. Good. Yeah, very similar. So my plan is to show you 1 and 3. Okay, so 1 is very simple. 3 is some technical thing I want to introduce at the same time to prove this. But now only 3 minutes. Okay. But then do you know how to use this limit law? You guys know how to use this? You guys know how to use limit law? Let me give you a small quiz. Maybe you should know, but I'm not sure you are asked in this kind of setting or not. So let's say I define my an to be this giant thing. Can you quickly tell me what's the limit? Can be based on what you learned in calculus. Can you tell me a limit when n go to infinity? Sorry. Say half of 2. Okay, so how do you show this? Actually, we should use our limit law. Okay. Yeah, so our limit law says what? If I know the individual term converges, I will know the whole term converges to where. Okay, so if you look at all the individual terms, actually they all converges. Okay. So pi is just viewing as a constant sequence pi. Okay, constant sequence pi. And then the 2 is also constant sequence 2. Maybe the non-trivial one is this limit of 2 to the minus n. Okay, what is it? And then I guess limit of 1 over n squared, we can view it as limit of 1 over n. Unless you know the limit of 1 over n squared, otherwise, maybe we just assume we know what is the limit of 1 over n. Okay, so maybe some lemma you need to do is you need to check that. Lemma. 2 lemma you need to do. So prove that 1 over n goes to 0 when n goes to 0, infinity, and then 1 over 2 to the n go to 0 also. Okay, when n go to infinity. Yeah, okay. Yeah, these 2 things here you need to do. Then if you know all these, then by limit law, it is just half the 2. Okay. So this is how you apply limit law. Yes. Question. Yes.
Limit of a fraction, then you
Correct.
the limit of the numerator and the limit divided by the limit of the numerator. What you do? It's like 0 over 0 is our form.
Yes, that's right. So
Once you check these, right? So once you check this, this term here cannot be 0, right? Can never be 0. So it makes sense to write this down. Yeah. And then you can use this to compute. You can use this to compute, and then to compute the Bn conversion, you need to compute the limit of this plus the limit of this. That's right. So this term can never be 0. Even this 0, 2 cannot be 0. So this term is very simple. Yeah. That's right. You need to check this Bn here cannot be 0. Yeah, sufficiently large. But then this one No matter what end you take, you can reduce.
Maybe I want to focus more on this two actually. Okay, so how do you show this two is the limit of this two is?
I think this one is easier. This one is easier based on what we know. I think this one is harder. This one is a bit harder. This one is a bit harder. Yeah. This one is a bit harder. I have proof in science. Maybe I try it first. Why it works. If you have question, then we can resume from here next week. Otherwise, you can learn yourself. Kind of technical. Probably need induction. Because we are trying to relate 2n back to n. Because this one is easy. This one is easy. Is this easier?
You know what you need to show to prove this? Maybe we can quickly talk about this. What do you need to show? You need to show something like 1 over epsilon 1 over n less than epsilon. But then this looks very like what? This looks very like what?
This n is natural number.
I guess.
Not like that code.
What is this?
Epsilon, real number, natural number, what is this? So this one is really all productive. And then this one you need to try and kind of relate back to this.
Yeah, okay. Okay. Any question?
Yeah, try to write the
Practice spreading the full argument. But the idea is Archimedes. I will have the solution in the notes. So later you can try and compare. Okay, any question? No? Okay, no, maybe we can stop here. And then next week we can resume with the proof of limit. Okay, see you tomorrow.